Okay, welcome to part two of game theory. In this lesson, what we're going to do is start by going through the most classic game studied in introductory game theory, which is called the prisoner's dilemma. Some of you may have seen this before. This is somewhat common it's a game that's commonly discussed in political science and other fields other than economics. So the prisoner's dilemma, the general setup of the prisoner's dilemma is two players, both held separately by the police for a crime that they're both accused of committing. So, as I usually say, you can pick your favorite criminals, Bonnie and Clyde, or two people from The Wire, or whatever you'd want. Imagine two criminals held separate by the police for a crime they're both accused of committing. In this scenario, each person, has two choices. They can deny their involvement in the crime, or they can confess their involvement in the crime. And in reality, whether they actually did the crime or not almost doesn't matter if you just start to assume that the numbers are valid. Both of the players know that the amount of time they spend in prison is going to depend both on the actions that they take, as an individual, and the actions that the opponent, the counterpart, takes. So, getting into a little bit more detail here, and getting into some specifics. So, the police will isolate the two prisoners. So they'll get the prisoners isolated, and they'll go up to one prisoner, which we'll call prisoner A. And they'll go in private to prisoner A, and they'll say, look, if you confess your crime, we'll have you testify against your opponent, and we'll give you somewhat of a lighter sentence than what you would get otherwise. So if you confess your crime, if your opponent denies the crime, we're going to use your testimony. You will only get out with a year in prison. That's much better than you could do otherwise. So if you confess the crime, 1 year in prison is what you'll get. We'll work this plea bargain out with you. If you confess and your opponent confesses, what the police would say to prisoner A here is, look, you're both confessing the crime, so we don't need either of you to testify, but since you're cooperating, instead of 10 years in prison, you'll only get 5 years in prison. So we'll limit your sentence somewhat for your confession and cooperation. At the same time, they'd say, look, if you deny the crime, if your opponent denies, you'll get 2 years in prison. And here's where you maybe have to suspend your disbelief a little bit. In the U.S. system, of course, the police don't just have the power to say, this is what you get. You could imagine that the police have pulled somebody over for some drug trafficking charge, these two people. But they both found a gun with each of them, and the gun would be 2 years, and that's a pretty easy case to solve. So the police would say, look, if your opponent denies, we're still getting you on the gun charge. You get 2 years in prison this way. If your opponent confesses, and if you choose to deny and your opponent chooses to confess, this is what the police would be saying, we're going to have your counterpart testify against you, and you're looking at 10 years in prison. So they've laid out pretty clearly to the prisoner what the options are. If the prisoner confesses, it's 1 year in prison. If the opponent denies, 5 if the opponent confesses. If the prisoner A denies, it's 2 years in prison if the counterpart denies, and 10 if the counterpart confesses. They say the same thing as well in a separate room to prisoner B. And if you've watched TV shows or movies, you've probably seen some interrogation scenes that look something like this, where police are trying to extract confessions from multiple different people who they suspect are involved in a plot. This case is just kind of simplifying, putting a few numbers on it. And the game is called the prisoner's dilemma. So this is all the information you need. Last time we showed the general setup of how to construct a payoff matrix. And you also, if you look through the textbook, there will be some good examples of payoff matrices. What I want you to do right now is use the information that we've just gone through, the information on your screen about what the police have said to prisoner A and at the same time said to prisoner B, and use this information to write out a payoff matrix. So now is a good time for you to pause this recording, and on your own on a piece of scratch paper, go ahead and try to write out the payoff matrix with the payoffs in there. Okay, I hope you've taken a shot. I hope you paused the recording for and taken a few minutes to try to write this out on your own. It's valuable, obviously. If you didn't do this, the biggest downfall is you don't get the practice of trying to mentally figure out, okay, how do I take this information and put it into a payoff matrix? The payoff matrix would look something like this. So you have prisoner A has two choices, to confess or deny. Prisoner B also has two choices, to confess or to deny. Then you have the job of putting the payoffs in there. Notice at the top here we have player A's prison sentence, player B's prison sentence up top. Well, if they both confess, recall what the police told them. Look, if you both confess, we obviously don't need you to testify, but we'll go light on you. You each get 5 years in prison. One of the key things that I see in people who are first writing this out is they'll maybe only put one number in the payoff matrix at the first time. But that's not correct. You need to have the payoff in both for player A, and that's the first 5, and for player B, and that's the second 5. In general, the row player, the player who chooses the up or down choices, is listed first, and we do note that up on this slide. The player who's choosing which column, left or right, will be listed second. So A is choosing, A's payoff is 5, B's payoff is 5. If they both deny as well, that one's also a little bit easier to sort out, as the police will tell them both, look, we can still get you on this gun charge, you each get 2 years in prison. So it's 2 and 2. If one of them confesses the crime and one of them denies the crime, though, this is where it gets a little bit different. Right? The police have made the offer to each one. Look, if you confess the crime, so we're going to player A, and player B denies the crime, well, we'd be at this outcome right here in the upper right quadrant. So if player A confesses the crime and player B denies the crime, the police say, player A, we're going to give you 1 year. At the same time, they've said to player B, look, if you deny and your opponent confesses, we're going to have your opponent testify against you. So player B gets 10 years in prison. So this upper right quadrant is showing us the payoff if player A confesses and player B denies the crime, 1-10. It's the exact opposite in the bottom right quadrant. Here it's where player B is confessing, so player B gets the 1-year sentence, but for testifying against player A, who now gets a 10-year prison sentence. So this is the way the payoff matrix for this particular game should look. Now if you put deny at top and confess on the bottom, that's perfectly fine. Should end up with the payoff matrix that just looks, the numbers will be in different spots, but the construction of where things should, when they both confess, it should be both 5. When they both deny, that should be both 2. The one who confesses against somebody who denies, the confessor gets 1 and the denier gets 10. So a couple of questions then to think about, and once again, you may want to pause this for a moment to think about these two questions. First question, what outcome would be the most efficient from the standpoint of the prisoners? And what outcome do you think would occur in this game? And for this, I want you to make the assumption that the only thing that matters is these payoffs that we see, that nothing else matters. What outcome do you think would occur? You may want to pause this for a moment to take some time to think about and jot down what you think the answers to these two questions would be. Okay, we'll get to the answers to those questions in just a moment. First, we want to go through a couple of definitions. This first one, a Pareto efficient outcome is an outcome where neither person can be better off without the other person being worse off. And this is likely, once again, this is probably a strange sounding definition. It is similar to our definition of efficiency when we talked about the production possibilities frontier. If you can recall back to that lesson. Pareto efficiency is a similar definition, but it still likely sounds pretty strange. A Pareto efficient outcome is an outcome where neither person can be better off without the other person being worse off. One good way to think about this is, how is this efficient? Imagine the opposite is true. If the opposite is true, you have an outcome where somebody could be made better off without harming anybody else. And if you're at an outcome where somebody could be made better off without harming anybody else, you're not at a good starting point, right? You should have moved to the outcome where you could make somebody better. The only way, if you're at an efficient outcome, to make some person better off is you have to take away from somebody else. So that's what we call a Pareto efficient outcome. It's one measure of efficiency. It's actually should be a pretty easy measure of efficiency to hit in society. If you can't hit Pareto efficiency, you have some major problems. So this is generally a pretty weak measure to hit, but as we see, we're not going to hit it some of the time within our games that we study in game theory. The second definition on this page, the Nash equilibrium, it's the non-cooperative outcome of the game. It is the best strategy for a person or a player given what the others are doing. So it takes the other player's choice as a given, and it assumes, could you be better off by switching your choice? So if one player's choice is up or down, and the other player's choice is up or down, each player is going to assume, okay, if we're at a starting point of up, up, each player has to assume the other player is staying with up, and then would I want to go to up or down? So it's the best strategy for a person given the other person's decision. The last sentence in here, at a Nash equilibrium, there is no incentive to deviate for any player. No player wants to change his or her choice given the actions of the other players. These two definitions are pretty important. These are two of the bigger concepts that we will be studying in this introductory lesson. And really, throughout all of game theory, Pareto efficiency and the Nash equilibrium come up over and over, even if you decide to take upper level game theory. So in this game, the Nash equilibrium is for each party to confess. The question we would obviously want to look at is, why is that the case? So each person within this game would confess, and that's what we call the Nash equilibrium. The question is why. To do this, I like to take a look at the other outcomes first. And recall, to be a Nash equilibrium, you have to be at an outcome and not want to switch to a different outcome. And what you need is really every player in the game doesn't want to switch. So what about the bottom right quadrant, where we have both of them getting a 2-year prison sentence? Well, both of these players here actually have an incentive to switch to a different choice, right? If player A goes from deny to confess, they'd go from a payoff of 2 years in prison to a payoff of 1 year in prison. Well, going from a payoff of 2 to 1, that's an improvement. Player A wants to switch. And really, seeing that's all we need to know that deny, or both players denying, is not a Nash equilibrium in the game. But player B, the same holds. If player B switches from deny to confess, player B goes from 2 years in prison to 1 year in prison. So in fact, for this one, both players want to switch their choice. Now, in the outcome where one of them confesses and one denies, I hope this would seem somewhat obvious that one of the players, this is their worst possible outcome. One of the players is getting 10 years in prison if they are denying and the opponent's confessing. So the player who's denying in this outcome, and here A is denying, B is confessing, A would want to switch to confess, right? Instead of 10 years in prison, 5 years in prison. At this other outcome where B gets 10 years in prison, B would want to switch from deny to confess, to go from 10 years in prison to 5 years in prison. So neither of those outcomes can be a Nash equilibrium because one of the players wants to switch his or her choice. Recall equilibrium as a stable point. You're stable. There's no incentive. There's no pressure to go somewhere else. Well, at these three outcomes we've just described, there is pressure to move. The players have pressure. Any player who's choosing deny has a pressure, can be better off by choosing confess. So what about the outcome where they both confess then? Well, if you're here, let's look at player A. Player A, given that B is choosing confess, player A could go from 5 years to 10 years in prison if player A switched. That's a pretty bad move, so player A will not want to switch his or her choice. Player B, if player B switched from confess to deny, player B would be switching from 5 years to 10 years as well. By switching from 5 years to 10 years, obviously that's a bad choice as well. Both player A and player B would want to stay at confess, and that is the Nash equilibrium of the game. So the Nash equilibrium is for each party to confess. The reason why, that's the only outcome where there's no incentive for somebody to switch his or her choice. Is this outcome Pareto efficient? Absolutely not. To see why, let's go back to the game again. If they both confess, which is what we expect the outcome of the game to be, that's our Nash equilibrium, they both get 5 years in prison. There is another outcome of the game that could give them both 2 years in prison, right? If they both denied the crime, they'd both have 2 years in prison. Instead, they both get 5 years in prison. Our definition for Pareto efficiency, can you make at least one player better off without harming anybody? Well, here, yes. And we could actually do better than that. Here, we could make both players better off. Nobody's being harmed. They both would be happier if they both denied the crime. So the Nash equilibrium, the outcome we expect in the game is for both to confess. It is not an efficient outcome, though. They would both be better off if they both denied the crime. So confess as the Nash equilibrium is not a Pareto efficient outcome. So in the prisoner's dilemma game, the Pareto efficient outcome is for both parties to deny. And in fact, and this is not something that's on the test, but the two outcomes where one is confessing and one is denying, those are actually also Pareto efficient outcomes as well. The reason those are Pareto efficient, if one of the players is getting their very best possible outcome, right, 1 year in prison, if you switched away from it, that player's worse off. So those two outcomes where one is confessing and one is denying, actually also a Pareto efficient outcome. What I'm worried more about on homeworks and on an exam is the equilibrium Pareto efficient? Is the Nash equilibrium Pareto efficient? Yes or no? Not look at every outcome and tell me if a specific outcome is Pareto efficient. So the prisoner's dilemma game, you can start to see why we call it a prisoner's dilemma. If they both denied, they're both better off. But they both actually have an incentive to confess. So they have a dilemma. What's better off for the individual here is not better off for them as a whole. So how do we determine the outcome of the games in general? And I think we kind of just talked through it a little bit. Determine what the player would do under any circumstance. So when we looked back at each of the 4 possible outcomes, we looked, would a player want to change his or her choice? So let's move back over to the game. So if player B were to confess, what would player A want to do? Well, if player B were to confess, player A has 2 choices here. Player A could get a payoff of 10 by denying or 5 by confessing. Player A will want to confess and get a payoff of 5. 5 years in prison is better than 10 years in prison. Well, what about if player B chooses to deny instead? Then player A has the choice of confessing for 2 years in prison, confessing for 1 year in prison or denying for 2 years in prison. Once again, confessing is the better choice. No matter what player B does here, we actually see player A gets a better payoff, fewer years in prison, by confessing the crime. 5 is lower than the 10, 1 is lower than the 2. Player B, and this game is symmetric, so you probably could deduce that the same will happen. It's the same for player B. If player A confesses, player B is looking at 10 years if he or she denies, versus 5 years if he or she confesses. Whereas if player A denies the crime, player B would be looking at 2 years by denying, 1 by confessing. So player B also will want to confess the crime regardless of what player A chooses to do. Skipping back ahead to the slide we were just on, we could use that information to see if it's a Nash equilibrium. We found it last time by looking at each individual square, each individual outcome, each of the 4 quadrants, and seeing does anybody want to switch. And that's a perfectly valid way to find the Nash equilibrium. The other way is to look for what we call dominant strategies. And we just actually talked through the idea of a dominant strategy. A dominant strategy occurs when a person or a player has an alternative that's preferable regardless of what his or her opponent does. So we just went through the game and found no matter what player B does, player A wants to confess. That means player A has a dominant strategy to confess. Player A will always confess. It doesn't matter whether player B chooses to deny or confess the crime. Player B, it's likewise. It doesn't matter what player A does. Player B will always want to confess. It's the payoff in terms of prison years is always smaller for player B to confess the crime than to deny the crime. So if a game has a dominant strategy, which this prisoner's dilemma game does have, becomes easy to find. You could look for a dominant strategy. You could look, does one player always want to take a particular action regardless of what the other player wants to do? And if that's the case, in this case, player A will always confess, player B will always confess. If you have a case like that, that tells you the Nash equilibrium. It tells you that the Nash equilibrium is player A is going to confess the crime and player B is going to confess the crime. So there are 2 alternative ways you could find the Nash equilibrium, either by going quadrant by quadrant or seeing if there are dominant strategies. There aren't always going to be dominant strategies, but if there are, that will point you directly to the Nash equilibrium. So in this game, both of the prisoners had a dominant strategy to confess, which means even if we didn't use the other method, we would know the Nash equilibrium is for both players to confess.